Okay, this is another one we'll use the prefix system for because we have two nonmetals. This would be dinitrogen tetraoxide, or you could say tetroxide, it wouldn't matter. So dinitrogen tetroxide. Okay, this is another ionic compound. We have a metal and a nonmetal. You will notice that the metal, barium, is representative. It's always 2+. Sulfate's 2-, so the formula is BaSO4. You simply name this barium sulfate. Here's another ionic compound with a polyatomic. Calcium is representative, it's always 2+. Hydroxide is always 1-, so that is the correct formula for calcium hydroxide. Alright, in this example you have zinc. Zinc is a transition metal, however it always has a 2+ charge, so you don't have to say zinc 2 because it's never anything other than 2. This would be zinc nitrite. Ionic compound with a representative metal, sodium, so you simply name this sodium chlorate. Okay, now we're going to practice writing some formulas from names. Ammonium is a polyatomic. Hope you guys have those memorized. Ammonium's NH4 with a 1+. Sulfate is SO4, 2-. And so when you cross them, you need 2 ammoniums, so you must put it in parentheses, otherwise it looks like 42. So NH4 parentheses 2, sulfate is SO4. Ammonium sulfate. Okay, diphosphorus hexoxide. Okay, so let's see, diphosphorus, you would have P2, and then hexaoxide would be O6. Okay, because this is a molecular compound, 2 nonmetals, you will not reduce to a 1 and 3, just leave it P2O6, and you don't cross them or anything, that's only with ionics. So for molecular, you just write it as it is, 2 phosphorus, 6 oxygens. Okay, aluminum phosphate, we know aluminum is always 3+. Phosphate, polyatomic ion, is PO4 3- because they are equal and opposite, they cancel. AlPO4 is aluminum phosphate. Zinc chloride, we know zinc is 2+. We know chloride is Cl, it's 1-, so the formula is ZnCl2. Okay, chromium 3 oxide, this tells me that the charge of chromium in this instance is 3+. Oxide is 2-, and so if you cross them, it's Cr2O3, chromium 3 oxide. Okay, calcium representative, it is always 2+. Nitrate, polyatomic that we have memorized, NO3, and it's 1-, so Ca NO3 parentheses 2, calcium nitrate. Okay, copper 1 chloride, this tells me that in this instance copper has a 1+ charge, chloride is 1-, so copper 1 chloride is CuCl. We have another molecular compound, carbon tetrachloride, so that means 1 carbon and 4 chlorines. Okay, the number of nitrogen atoms present, notice, and this would be called iron 2 nitrate. In this example, there are only 2 nitrogens. Coincidentally, if you're curious, there is only 1 iron. There would be 6 oxygens, but it's asking for nitrogen 2. Alright, we're going to do some balancing and identifying reaction types. Before we balance this, let me put the arrow in there. let's look at this. This is propane plus oxygen yields carbon dioxide and water. So we have an organic molecule, one that contains carbon and hydrogen, combining with oxygen, forming carbon dioxide and water. This is a combustion reaction. This is a complex combustion, but it is a combustion reaction. So let's balance. Let's do our atom inventory. There are 3 carbons, there are 8 hydrogens, there are 2 oxygens. On this side, 1 carbon, 2 hydrogens, 3 oxygens. Okay, so if I put a 3 here, this is going to make this 3. Oxygen now is 2 times 3, which is 6, plus 1 is 7. Fair enough. Okay, hydrogen, I have 8 and I have 2, so if I put a coefficient of 4 here, this becomes 8. And now let's look at our oxygen. 2 times 3, which is 6, plus 4 is 10. Okay, we can easily get 10 oxygen on this side by placing a 5 there. So there is your balanced formula equation. 3 carbons, 8 hydrogen, 10 oxygen on each side, coefficients of 1, 5, 3, and 4. Okay, in this reaction we have ammonia combining with sulfuric acid to form ammonium sulfate. Anytime you have 2 things combining to make 1, that is an example of a synthesis. You may also call it composition, either one, but I'll call it a synthesis. Alright, let's do our balancing. Let's see, 1 nitrogen. We have 5 hydrogens, 1 sulfur, 4 oxygen. On the product side, we have 2 nitrogens. Hydrogen, I have 8. I have 1 sulfur and 4 oxygens. This is hydrogen. Okay, so let's see here. If I put a 2 here, this is going to become 2 nitrogens. Hydrogen is now 2 times 3, which is 6, plus 2, 8. Lo and behold, we have balanced it with 1 coefficient. Okay, here's an example where we have 1 substance breaking down into 2. This is indicative of a decomposition reaction, where one thing is falling apart or being torn apart into 2 or more things. Let's take a look here. Very quickly, if I put a 2 here, I have 6 oxygen on both sides. I put a 3 here. 2 goes in front of the potassium chloride. Okay, in this example we have zinc combining with hydrochloric acid, and so this is going to be representative of a single replacement reaction. We're going to have zinc taking the place of one of the following elements. It's going to really change places with hydrogen because zinc forms positive cations. It's going to go with a negative chloride. So the formula for zinc chloride is ZnCl2 because zinc is 2 plus always, chlorine is 1 minus. And then what's left over is hydrogen. But hydrogen is not simply H. It's got to be H2. You have to identify that that is indeed a polyatomic ion. There are 7 elements that are never found by themselves. You can remember it by going to 7, making a 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and their goofy friend hydrogen. Or, if you prefer the term Brinkelhoff twins, whatever floats your boat. To balance this, fairly straightforward. Put a 2 in front of the hydrochloric acid, and we're balanced. This is going to be another example of a synthesis reaction. We have 2 things that are going to combine and to make 1. Potassium is 1 plus, chlorine is 1 minus, so the formula for potassium chloride is KCl. So don't get your pants in a bunch and say, well, what about that 2? We fix it with coefficients. So 2 potassium chlorides, we'll put a 2 in front of the potassium. Now everything's balanced. Okay, this one I have 2 compounds that are both ionic, both have a cation and an anion, so this is going to be a double replacement reaction. Basically, the cation of the first is going to recombine with the anion of the second, and vice versa. The cation of the second is going to go with the anion of the first. It's important to note that you always list the metal, the positive ion first, the anion is always second. So aluminum is 3 plus, sulfate is 2 minus, so therefore the formula for aluminum sulfate is Al2SO4 parentheses 3, so that's aluminum sulfate, and what's left over is you have potassium, which is 1 plus, and bromine, which is 1 minus, so it's KBr is potassium bromide. Now as far as balancing is concerned, okay, if I put a 3 here, I'll have 3 sulfates on both sides, if I put a, let's see, a 2 here, that's going to give me 2 aluminums on both sides. And now to balance the potassium and the bromine, I put a 6 here. 6 potassium, 6 bromines. There is your balanced formula reaction. A catalyst in a chemical reaction is basically a substance that needs to be present in order for a reaction to occur. Largely how it functions is the fact that it lowers the amount of energy required for a reaction to initiate, so it lowers what's called the activation energy. A common example of this in your car, in the exhaust system, you have a thing called a catalytic converter. Inside there is platinum metal in the form of kind of a platinum sponge that basically takes carbon monoxide and turns it into carbon dioxide. The thing about a catalyst, it is not consumed, so it needs to be present in order for the reaction to occur, but it's not a reactant, it's not a product, it's just there. Very commonly, so like in this example, you would write PT above the arrow. That indicates that platinum is a catalyst. It's not really taking part of the reaction as far as like a reactant or product. It's not going to be present in either sense, but it needs to be present in order for the reaction to occur. So a catalyst is generally written, the formula will be written above the yield sign. The main difference between an endothermic and exothermic reaction is basically it's just tracking the motion of heat. So if I have like some reaction taking place here in the beaker, so let's say here's some solution. Okay, if you put your hand here, here's your hand, and the heat is leaving the system and entering the surroundings, which is like your hand, you experience this as an exothermic reaction. Heat is leaving the reaction, leaving the system, and entering the surroundings. Exothermic, heat is exiting. Endothermic is the exact opposite. So here's your beaker again with some solution. Here's your hand. Okay, as you touch it, it's going to feel cold because what it is doing is it is absorbing heat from the surroundings. And so this would be an endothermic reaction. Heat is leaving, or excuse me, heat is entering the system from its surroundings. So like an example of each of these, like an exothermic, would be like one of those hand warmers. It's got the little disc in there that you pop, and it feels hot. Endothermic would be like one of those instant ice packs where you break the capsule inside, and the substance feels cool because it is absorbing heat from the surroundings, like being your ankle, if you twist your ankle or your hand or whatever.